Okay, guys, welcome to Let's Get to the Marks. We're looking at AS Chemistry, Paper 2, Organic and Physical. This is the 2018 paper. There's 8 written questions plus a section B, which is the MCQ. You'll find the link to this in the description for the brilliant Physics and Maths Shooter website. It's going to have the paper and the mark scheme on there. You might have to do a little bit of looking, but I've put the link to the page on the website where you're going to find that. Let's get straight into it. Don't forget, I recommend at the start of each question, pause the video, then un I can't talk. Pause the video, have a go on a scrap bit of paper, right? With a pen, with a pencil, whatever. You can chuck the paper away at the end. It just makes it a little bit more active. Just bullet point what you think the answers are, then unpause and check your answers and watch the walkthrough for the explanation of how to get to the answer. All right, enough of my whiffle waffle waffle. Let's get on with the actual walkthrough. Question one, hydrogen peroxide solution decomposes slowly to form water and oxygen. The reaction is much faster in the presence of a manganese 4 oxide catalyst. We've got the equation. We've got 2 molecules of hydrogen peroxide in aqueous. Break down to form 2 water molecules liquid and 1 oxygen molecule gas. 3 experiments shown in table 1 were carried out to investigate how the volume of oxygen produced varied over time under different conditions. The same mass of the catalyst was used in each experiment. So we've got experiment 1, 2, and 3. One had a 1 mole per decimeter conc and a volume of 50 centimeter cubed, temperature of 20 degrees, and it used the catalyst in the form of lumps. The second experiment, the concentration's the same, the volume's the same, the temp's the same, but this time they powdered the catalyst. And then experiment 3, we're using half the concentration, volume is the same, temp's the same, and they're using lumps again. Right, the first question, we're shown the graph with the volume of oxygen against time. It's a typical graph where once the reactants run out, or as they start to run out, we get a curve on the volume of oxygen produced, and then it levels off when there are no more reactants left, or when either of the reactants has run out. In this case, there's only one. 1.1, explain in general terms how a catalyst increases the rate of reaction. So we should all know that catalysts provide an alternative route for the reaction. And what is it about this route that is special? You should know the route has a lower activation energy. And that will get 2 marks. Okay, the next question says, draw 2 lines on figure 1 to show how the volume of oxygen collected varied with time in experiments 2 and 3. Label each line with the experiment number, and that is worth 2 marks. There's what's going on with the old PC. Okay, we need to draw a line for experiment 2 and 3. So experiment 2, what is the difference? It's powdered instead of lumps. So it's going to react faster. But is it going to end up totally higher? No. Concentration is the same. So we're going to run out of reactant and level off at the exact same amount. So you're going to get the mark here for 2 things. Having it react higher, so the line needs to be steeper, and then it will run out of reactant first because it's reacting faster at a higher rate of reaction, but it's going to end up at the exact same place. Okay, shouldn't be a wobble in the line there, but there we go. That is line number 2. Now let's look at experiment 3. This time we're using lumps, the same temp, same volume, so everything's the same. So we'd expect the reaction rate to be similar, except for we've got half the concentration, which means slightly less collisions. So what we're doing here, we're coming up like that, and then we're separating. And I've gone too high there. Why have I gone too high? Because we can only make half the amount of product. So I need to end up over here like that. Just about got that in right. Okay, so we want to end up with half the amount of product because we have half the number of particles to collide. And that means that the reaction is going to be slightly slower. Even though the same temperature and volume, it's going to be slightly less collisions as we have half the concentration. So there we go. Right, line 2, line 3, that's going to get you a mark for each of them. Let's move on to the next bit. Down here, 1.3, final part to the question, explain in terms of collision theory the effect of increasing the concentration of hydrogen peroxide on the rate of reaction. So what's the effect of increasing the conc of hydrogen peroxide on the rate of reaction? And this time we've got to explain it. So if you increase the conc, the rate of reaction increases. So increasing the concentration increases the rate of reaction. And the explanation for that is we're going to have more particles in the same space. So more reactant particle. Oh my gosh, I can't spell reactant. More reactant particles in the same space, same volume, which is what happens when you increase the concentration. And that's your first mark. What's the second mark? This leads to a higher frequency of successful collisions. Um, Higher frequency of successful collisions. Now, another way to say frequency is a higher frequency of, or sorry, a higher amount of successful collisions per second. So as long as you give collisions per time, that's the same as saying frequency. So higher frequency of successful collisions. Why? Because we have more reactant particles in the same space or same volume. There we go. All right, guys, that's question one done. Let's move on to question two. So for question two, I'm going to read through this. Citric acid, C3H5O, COOH, 3 lots, occurs naturally in many fruits and can also be synthesized in the laboratory for use as food flavoring. A student analyzed the sample of citric acid to determine its percentage purity. The student dissolved 780 milligrams of impure citric acid in water to prepare 250 centimeter cubed of a solution in a volumetric flask. The student titrated 25 centimeter cube samples of this solution with 0.05 mole per decimeter sodium hydroxide solution using phenolphthalein as the indicator. We have the equation for this. The only unusual thing immediately I would be drawn to in this equation is that we have 3 carboxylic acid groups on our citric acid. And that means, of course, and you can see it quite clearly in the ratio, our ratio of acid to alkali is 1 to 3 to the sodium hydroxide, because each OH needs to react with one of the H's on the 3 carboxylic acid groups. Now, what does that tell me? I've been given the ratio and a load of other data, so I kind of know the questions are coming up, and you should try this when you're working through papers. And anytime you're doing a practice question, you should be testing yourself as you go through the STEM. I think I know what this is about. You should be making notes on the paper. So what we've read through so far, I'd be thinking, right, percentage purity, I might be doing that. I'd be going, oh, look, I've been told about 784 milligrams. I might have to convert that to grams. And that is a mass. So I'd write an M there. And then I'd be like, oh, prepare 250 centimeter cubed solution in a volumetric flask. And then the student titrated 25 centimeters from that 250. That means I've had a 10 times dilution. So I might have to multiply up or divide, but there's something I'm going to have to do with 10 times. So I've had a 10 times dilution. I then come along here and they've given me 0.05 mole per decimeter, and I'd write a C there and be like, that's the concentration. So what we're doing, and the 25 centimeter cubed is the volume. What we're doing is we're making notes as we go through a STEM, and you should be doing this mentally, if not physically writing on your exam paper, which I think you should do, but you might not be able to because you're go working on a screen. So just be making notes mentally. Oh yeah, I'm probably going to need to do a mole calculation. Oh, I might have to do a mass conversion. Oh, there's a dilution, so I'll probably have to times up. Oh, the ratio's 1 to 3. You should be taking all of this in as you're reading through the question. Anywho, 2.1, the student rinsed the burette before filling it with sodium hydroxide solution. State why the student should use sodium hydroxide solution rather than water for the final rinse of the burette. Right, when you rinse out a burette, if you leave water clinging to the inside of the burette, when you fill it with your sodium hydroxide of a known concentration, what's going to happen to that known concentration? It's going to be diluted and not the concentration that it says on the tin. So, and that's going to affect your titra. If you have a weaker or a lower decrease in the concentration, so if I have 0.5 moles instead of 0.6 moles, then my titer with the 0.5 moles is going to be larger. I'm going to need more of it to neutralize the acid. So, whoops. If we rinse with water, it will decrease the concentration of sodium hydroxide, and this will increase the titer. Now, it's not always a bad idea to if you know that you're purposefully decreasing the concentration, that's not always a bad idea. That can enable you to have more accurate results with less error because you have a bigger titer. Anywho, let's move on. That's one mark there. Now we're going down to 2.2. The student carried out several titrations. The results are shown in table 2. Complete table 2 to show the titra in each titration. So we got the final reading, the start reading, what's the titra? So for the first one, we've got 25.2. So it's literally just fill these in. We've got 23.95, but it was 0.05 at the start. So this is 23.90. You're just finding the difference between the final and start reading. I need my calculator for this because I'm not too smart on this. 47.65, take away 23.95, and we have a mean titra here of 23.70. And then I've got 24.10, take away 0.10. So we're going to go 24.10, take away 0.10 equals 24. 0.00. Now, calculate the mean titra using the concordant results. Give your answer to the appropriate number of significant figures. Which set of results here are concordant? Well, first of all, we don't need the rough titration, okay? You never use that in the calculation for your mean titra. And what I'd be looking at here is 23.90 and 24. They are like 0.1 within each other, and that is good enough to be concordant. The 23.70 is only 0. It's 0.2 away from the 23.90, so it's not good enough. So we're not going to include that in our titra. So to calculate the mean titra, we're just going to do 23.90. We're going to add that to 24.00. We're going to divide by 2, and we're going to get 23.95 centimeter cubed. Okay, beautiful. That's our mean titra. That's going to get us 2 marks. We're going to need that number later on because with titrations, you're always going to use the titra. So 2.4 says 1 mark. The total uncertainty when using the burette is plus 0.15. This is the combination of the uncertainties at the start and the final reading. So they've already calculated the total for us and the determination of the endpoint. Use your answer to 2.3 to calculate the percentage uncertainty for the use of the burette in this experiment. They've told us that they've taken into account all the different readings, the final and start reading. So we are going to just do 0.15. And we are going to divide that by our mean titra, 23.95. And we're going to times 100, smash that in the old calculator, and we can find out our uncertainty. And it is 0.626. We want this as a percentage. I'm going to round that to 0.63. Why? Because the 6 is bigger. So we're going to pump that 2 up to 3. There we go. And that's going to get us a mark. Okay, we're on to 2.5. Use your answer to question 2.3. That's the 23.95 again. Find the mass in milligrams of citric acid dissolved in 250 centimeter cubed of the solution. So the relative MR is 192. Now, my first things first, we had 23.95 was our mean titra for sodium hydroxide. And what was the concentration? The student titrated 25 centimeter samples of the citric acid. So we know we got 25 centimeter citric acid. They titrated that with 0.05 mole per decimeter sodium hydroxide. Okay, here we go. So we're going to need to do N over C times V. Your lovely titration. You always need that in titrations. So what I'm going to do, I want to find the moles. I want to do conc times volume. Let's not forget that volume needs to be in decimeters. You're A-level chemist, so you're just going to get into that habit. 23.95 divided by 1,000. That's going to give me, you could call that 0.02395. That is my volume. Going to times that by my conc, which was 0.05 for sodium hydroxide. And that is the conc. And that is going to give me my moles. And my moles are going to end up being one, oh my gosh, that is some ugly dot. 1.1975 times 10 to the minus 3. So now I have, and I'm going to have scored a mark there for my moles of sodium hydroxide. So you're going to have picked up your first out the 3 marks for working out the moles of sodium hydroxide. So divide moles by 3. So what we're going to do here, folks, I long that out. We're going to do, we're going to take our moles 1.19 75 times 10 to the minus 3, and we're going to divide those by 3 to get the moles of citric acid. So our moles of citric acid are going to end up being 3.99, and it's times 10 to the minus 4. So we've got less moles of citric acid, obviously 3 times less moles. But now let's remember that these citric acid moles were in how much? This is the trick. They were in 25 centimeter cubed. They were in 25 centimeter cubed of solution, because we only use the 25 centimeter sample from the 250. They've asked us to find the mass in 250, right? They want the mass in 250. So we need to times this by 10. So we're actually going to have, if I zing that there, we're going to have 3.99 times 10 to the minus 3 moles of citric acid. I need to use my other triangle. So what's the other triangle? You know the coup. It's mass over mR times moles. I think they gave us the mR. They did. Look, it's right there. So it's always a clue that you're going to be using that triangle. So now I know the moles. I want to times that by mR, which is 192. And that is going to give me the mass in grams of citric acid, the moles of citric acid in the 250, and I times that by the 192, which is the MR, I'm going to get 0.76608. Now, bear in mind that this is grams because mass is always in grams, and they want us to work it out into milligrams. So I need to times that by 1,000 to get my final answer and to pick up the last mark. So it's going to be 766.08. We could just round that to 3 sig, so I would just do 766, get rid of that thing there. That's probably what they're more likely looking for. Calculate the percentage purity. So all we've got to do there is say, what was the total mass in milligrams? I think it was 784. So we're going to do like 784. We're going to do 766 divided by 784 times 100, and we've got the purity. Lovely, bubbly. And what does that equal? Let's check it out. 766 divided by 784 equals that times 100 equals 97.7%. And here we go. Bosh. Okay, let's look at question 3. So, this question is about enthalpy changes. 3.1. When ethanoic acid reacts with sodium hydroxide, the enthalpy change is minus 56.1 kilojoule per mole. Calculate the temperature rise when 25 centimeter cubed of 2 mole per decimeter aqueous ethanoic acid reacts with 25 centimeter cubed of 2 mole per decimeter aqueous sodium hydroxide. Assume that both solutions have the same initial temperature, have a density of 1 gram per centimeter cubed, and a specific heat capacity of 4.18 joule. The units for specific heat capacity, and it's 4 marks. So what I would do is I'll bust out my highlighter pen, because when you read stems of questions, you should always be making a note as you go through of the different values and bits of data and information you've been given, and eventually you'll train yourself so when you spot a question, you can immediately, before you even need to be able to take in what the question's about, you will understand. So we've been given delta H over here. We've also been given an equation. I immediately want to know my ratios. So my reactants are in a 1-to-1. I've also over here, bada bada bing, bada bada boom. I've also been given 25 centimeter cube. What kind of unit is that? That's a volume. And I've been given mole per decimeter. What kind of unit is that? That's a concentration. Immediately my brain is thinking N over C times V. Okay, so this is how you need to be thinking. Assume that both solutions have the same initial temperature. So we're talking about initial temperature, have a density of 1 gram So we've been given D for density. As soon as I'm given density, I might be thinking density equals mass divided by volume. And I've been given the specific heat capacity, little baby c. Right, let me just zing down and see what the actual blooming question is. Temperature rise. Right, we're calculating the temperature rise. It did say calculate the temperature rise right there. So stupid old me missed that. Look, calculate the temperature rise. That's always the most important thing. So they want us to calculate the change in temperature, delta T. Okay. And I've been given the initial temperature. So given all of this information, we start to piece together, even if you're finding things difficult, you can start to piece together what you've got to do. So the fact that we've been given the specific heat capacity and I need delta T tells me we're going to have to use Q equals MC delta T. Okay. Um, so you might be thinking, well, what have moles got to do with that? Well, let's rearrange that to find the temperature rise. I need to do Q over MC, and that equals delta T, and that is going to give us our 4 marks when we get that answer there. And we look and we go, well, where's the mass? No one has given me the mass. So what I need to do is use this to find the mass. So the density is 1 gram per centimeter cubed. And if I need to find the mass, I need to rearrange that into a triangle, which you can do like this, mass over D times V. So I want my density times my volume, and it will give me my mass, my M. So the overall volume, there's 2 lots of 25, so it's 50. So I'm going to do 50. Whoa, whoa, whoa. I'm going to do 1 times 50, and that is going to give me a mass of 50 grams. So I now know I've got Q over 50G. Oh, I love 50 Gs. And times that by 4.18. Why 4.18? That is the little c. That's the specific heat capacity. Now I just need to find what is Q. And then we can work out our delta T. Well, you might think, is Q the energy is minus 56? No, because energy Q is always measured in joules. Q is energy in joules, the energy transferred in joules to be specific. So I've got to do 2 things to this energy, this kilojoule per mole, to turn it back into just J. I need to remove the K and I need to remove the divided by moles. So how am I going to do that? Well, first of all, we're going to times 1000 to remove the K, and that is going to get me 56,100 joules, but I'm still in mole to the -1. So I want to remove moles. So how are we going to remove moles? Well, in order to remove moles, I must times by moles. I need to times it by the number of moles because that is divide by moles, mole to the -1. So I need to times by mole. Mole times mole to the -1 gets rid of the mole to the -1. So I need to calculate moles, and I can do that by C times V. And you might say, well, the concentration is 2 for each and the volume is 25 for each. So how do we work that out? Well, we're just going to do any one of the reactants. We just need to find, it's a 1-to-1 reaction, so I just need to find the moles of one of them. So I'm going to do 25 divided by 1000, and of course that is the volume, and I'm going to times that by the concentration, which is 2. So technically I'm doing 0.025 times 2, which equals 0.050 or 0.05. That is my moles. So I now need to do 0.05 0.05 times, that looks ugly. I used the wrong, I used the 0, times 56,100. And that's just going to give me the joules. So let's smash that in the calculator. And we're going to get 2,805 joules. Beautiful. Now that is my Q. So I now just need to do whip out the final yeah, can't speak. Whip out the final bit, and that is 2,805 over 50 times 4.184. Definitely make sure you bash in the brackets, because if you don't do brackets, sometimes your old scientific calculator will give you a dodgy answer, and that should come up with 13.42. That is my delta T, my temperature rise. Now that is going to get me 4 beautiful marks. Okay, so lovely jubbly. Yeah, you're going to get a mark for rearranging the equation. You're going to get a mark for working out that what the mass was. You're going to get a mark for um, timesing by 1,000 and working out the joules. You're going to get a mark for timesing by the moles. Diddly dee, diddly da. Essentially, 4 lovely marks. Now let's zing on to the next part of the question. Oh, good gosh, we got a graph. Oh my gosh. 3.2, a student recorded the temperature of aqueous ethanoic acid in a polystyrene cup for 3 minutes. We know why they use polystyrene cups. If you're recording a temperature, it's a good insulator. As soon as I'm reading a STEM, it might have nothing to do with the question. It doesn't look like it is because it's giving me a calculation. Might have nothing to do with the question, but I just like to test myself. Oh, imagine this was asking, why is our result not as good? We didn't use a polystyrene cup kind of thing. We used a glass beaker, whatever. I like to be thinking the whole time. At the 4th minute, the student added sodium hydrogen carbonate. So at minute 4 on this graph, they added the sodium hydrogen carbonate to the acid. So we can see here is where they added it. The student stirred the mixture with a glass rod, I presume, and carried on recording the temperature every minute for several minutes. Look, we've got 5, 6, 7, 8, 9, 10, 11. The student's measurements are shown in figure 2. Here we go. A best line. Oh my gosh, I can't speak. A best fit line showing the temperature before mixing was drawn. Here's the temperature before mixing, all at 17 degrees. Draw an appropriate best fit line on figure 2 and use it to find the temperature change at the time of mixing. So they told us that they mixed it here at 4 minutes. This is our time of mixing. We don't know the temperature at that time because they were doing stirring with a rod and what else. So what we have to do here, folks, is when you do these experiments and you need to predict the temperature at the time of addition of a solid or at time of mixing, in this case, we've got the acid mixed with some solid sodium hydrogen carbonate. First of all, you take these initial temperature readings, which they did. Why do they do that? To make sure the temperature is constant. We're at equilibrium, and that will just be the acid in the cup. Then they add the solid. The temperature will change. Now, we don't know if the highest temperature or lowest temperature is recorded in the first 10 seconds after the mixing. So what we need to do is find the general trend. And the general trend, look, there's one out there, but the general trend is like this. And what I'm going to do, I found the general trend. I'm going to draw a line down here. Okay. And this is called extrapolation. We're going to find the general trend. We're going to draw a line through these crosses. My line is pop. So I'm going to have a go again. Draw the line through the crosses and bring that down to here. And where it intersects, this is the initial temperature, the IT, and this is basically our starting temp. So what I need to do here, guys, is work out where that's crossed that line, and that is my initial temperature upon mixing. So that is my initial temp. So it dropped from 17 at the time of mixing to, what is that, 11? Each one of these is 0.2. So 11.2, 11.4. I'm going for 11.5 there. And so if I do 17 minus 11.5, oh my gosh, oh my good gosh, I'm all over the place here. So that is going to give me what, 5.5? What's the temperature change? Temperature change at the time of mixing, I think it's 5.5, but maybe my maths is terrible. So yeah, 5.5. And the examiner is going to mark that based on your graph and where you have extrapolated your lines. And these are your extrapolation lines, this line here and this line here. And they're going to check that. So bish bash bosh, all good. Okie dokie, let's get on with question four. So, what do we want to do here? The alkanes nonane 2,4-dimethylheptane are structural isomers with the molecular formula C9H20. They are both found in crude oil and can be separated by the old fractional distillation. Both can be used in fuels or cracked to form other products. So, we have nonane here. Boiling point's 151, and we have 2,4-dimethylheptane here. Boiling point's 134, and they're both isomers, so they both have the same molecular formula, which means they have the same number of each element in the compound. 4.1, state the general formula of an alkane containing N carbon atoms. Deduce an expression for the relative molecular mass MR of an alkane in terms of N, and it's worth 2 marks. So what we got to do here, right, the general formula for alkanes, that is a lovely, easy mark. You think that is AS chemistry, you should know this at GCSE. So CnH2n, he says, nearly forgetting, plus 2. And that's going to get us the first mark for the general formula for alkanes. Now it's saying we need to make an expression for the relative molecular mass of an alkane in terms of N. So we're looking at really the MR. So carbon is 12, isn't it? Hydrogen equals 1, but we've got 2 of them. So technically, if you had 1 carbon, you'd have 12 plus 2 for the 2 hydrogens. So that's 14 N plus 2. So yeah, 14 times N plus 2. So 14 times 1 plus 2. So for example, let's say our formula was C2 H6, right? Then it would be 14 times 2, because N is 2 there. 14 times 2 plus 2. So that would be 14 times 2 is 28, plus 2 is 30. And if you check that, 2 times 12 is 24, plus the 6 is 30. Yeah, so that is our formula for working out the MR. 14 times the number of carbons, which is N plus 2. And that will give you the answer, the correct MR. So there we go. Enough whiffle, waffle, waffle. Let's zing on. Right, 4.2. Explain why nonane has a higher boiling point than 2,4-dimethylheptane. So straight away, what's the difference? Well, if we look at this one, it has a lower boiling point, and the only difference, they've got the exact same size, same number of electrons. So we can't say, oh, this one's got more electrons, therefore more van der Waals forces. We can't say that. They have the same number of electrons. The difference is that 2,4-dimethylheptane has branches, and how does that affect the intermolecular forces? So we will get on and explain that down here. So, bada bing, 2,4-dimethyl heptane, why am I writing in capitals? Take caps lock off, Tom. Has branches, okay, or is branched. So it has branches or is branched. Therefore, the molecules cannot get as close. So it has weaker IMF. You can't use abbreviations, but intermolecular forces or van der Waals forces. How do you spell van der Waals? What is it? Is it VDWS? So weaker van der Waals forces, weaker intermolecular forces, and that will get me the mark. Yeah. Okay, 4.3, give an equation for the complete combustion of nonane. These are the easiest equations in the world, combustion equations. So nonane, as far as we were concerned, was C9H20. Combustion is complete, so we need oxygen. And complete combustion always, if it is of a hydrocarbon, produces carbon dioxide and water. So all I need to do now is balance it. So I've got C9 here. So I want 9 carbon dioxides. I've got, oh my gosh, what the hell is that? H20. I was looking at it as H2O. It really rocked my brain there. So I've got 20 of them. So I need 10 water molecules to make 20 hydrogens over there. Beautiful. Now that's 10 times O, so that's 10 oxygens, and 9 times 2 is 18. So I've got 28 oxygens over here. So I need to bus off 14 in front of the O2 there. And that gets me the mark. Lovely. Let's read the next question. Nonane is often found in fuel for jet engines. Combustion in jet engines produces pollutants, including nitrogen monoxide. Explain how this nitrogen monoxide is formed. So you're looking at the engine gets very hot, so very high temperature. So on the mark scheme, they're going to talk about there being a very high temperature, and it's the metal in the engine that gets really hot. And then, of course, in the air, you have oxygen and you have nitrogen. And so we want to say nitrogen and oxygen from the air or atmosphere, from the atmosphere or air react on the hot metal engine. So that they react together. So we get a kind of like N2 plus O2. Both of these are gases in the air, and of course they make NO, nitrogen monoxide. They can make other combinations, nitrogen dioxide, nitrogen trioxide, all those kind of pollutants which cause respiratory illness and stuff like that. Okay, let's move on. Zinging down. Nonane can be cracked to perform large quantities of propene. Name the type of cracking used. So this is going to be thermolytic cracking, or you can just call it thermal cracking. Either one will get you the mark. So it's where you use a very high temperature and you're going to produce some alkenes. Okay. 4.6, the main use of propene formed from cracking is to make polypropene. Draw the repeating unit of polypropene. So I'm going to go through the common mistake here. Sometimes it's much hard. That's not so bad, actually, what they've asked for there. But let me just show you what can sort of mess people over. And that is, so I'm just drawing a molecule of propene here, right? Just check that I've put 4 bonds around it. Or 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Okay. The thing to remember with drawing your repeat unit of polymers is I always use brackets. And I always draw the carbon double bond in there. But remember, we're going to remove the double bonds opened up. So we're removing one of the double bond. And the reason I start with this and my brackets and my lines outside the brackets is now I know I can't be stupid and try and put CH3 there because that isn't going to work. So what we have to do is tuck our CH3, depending on where the space is, into the appropriate place. So my CH3 is going to be there. And then I'm just going to pile my 3 H's on there and there. So just watch out for that. If they give you a structural formula like that, only put, it's all got to be focused around the carbons from the double bond. So the way that I don't allow myself to make a mistake is by putting the brackets as soon as I've drawn the CC, and that sorts me right out. Okay. Okay, question 5. A hydrocarbon contains 87.8% biomass of carbon and has a relative molecular mass of 82. The hydrocarbon decolorizes bromine water. Determine the empirical and molecular formula of the hydrocarbon. Suggests 2 possible structures of the hydrocarbon. Name the type of reaction taking place when the bromine water reacts with the hydrocarbon, and this is worth 6 marks. We have to determine the empirical formula and the molecular formula for the hydrocarbon. So let's start off with the empirical formula. 87.8% is carbon. So if we do 100 minus 87.8, smash that in the calculator if you're dumb like me and you can't do that in your head. And you're going to get 12.2. So we now know that there is 12.2% hydrogen and 87.8% carbon. So in order to work out the empirical formula, you can pretend like these are grams. So you've got like 87.8 grams or 12.2 grams and you're working out moles. You can do it however you like, but you're going to do the percentage over the AR of that particular element. So for carbon, the AR is 12, and for hydrogen, the AR is 1. So that is our first step. And 87.8 divided by 12 equals 7.31. And 12.2 divided by 1 obviously equals 12.2. We now need to divide both by the smallest. So we go 12.2 by 7.31 and 7.31 by 7.31. We get 1 for the ratio of the carbon. And if we do 12.2 by 7.31, we get 1.66 for the hydrogen. So now that we've worked out that 7.31 divided by 7.31 is 1 and 12.2 divided by 7.31 is 1.66, we need to times them by a whole number in order to get these both to whole numbers, because this one 1.66 just won't do. We want to get it close to a whole number. So if I times by 2, I'm going to get 2 there, and I'm going to get like 3.3. 3.3 is not good enough. So then if I times by 3, I'm going to get C3. And if you times that by 3, you're going to get 4.98, which is 0.02 or whatever away. So that is good enough. So C3H5. The reason is if I times 3 times 1.66, you might say, oh, it's not a whole number. Well, it's close enough. It's like 4.98. So this is the empirical formula. Now, empirical formula. I can't spell it. Oh my gosh, days, what's going on? So that is the empirical formula. Now, when I add that up, you go 3 times 12 is 36 plus 5 equals 41. Well, that doesn't equal what we were told about the MR is 82. Look, the MR is 82 and the empirical formula is 41. So if I do 81 divided 82, not 81, what the hell? 82 divided by 41 equals 2. So I need to times the empirical formula by 2. So if I go 2 times C3H5, I'm actually going to get the molecular formula, and the molecular formula is going to be C6H10. So we've now cracked the first couple of parts of this. We've done the empirical formula. We've worked out the molecular formula. Suggest 2 possible structures for the hydrocarbon. Name the type of reaction taking place when bromine reacts with the hydrocarbon. Well, normally it says here the hydrocarbon decolorizes bromine water. What does that tell you? That tells me double bond. I don't know what it tells you. And then you think alkenes. So we would ask ourselves a question, is it an alkene? And I'd say, well, alkenes, as you know, have the general formula CnH2n, but this doesn't fit the alkene general formula. C6H10, it should be C6H12 if it's an alkene that's decolorized the bromine water. So it definitely has a double bond, but it's not an alkene. So then I start thinking, oh, well, maybe it is an alkene, but it's a diene. So maybe it's a diene. Uh, Maybe it is a diene or a cycloalkene, because they're going to have less hydrogen. If you're a diene, you've got 2 double bonds, and if you're a cycloalkene, you're going to have less double bonds. So what I would do from here, of course, name the type of reaction taking place when bromine reacts with the hydrocarbon. This is going to be an addition reaction. It's going to be like electrophilic addition. Is it electrophilic addition or nucleophilic addition? It's addition anyway. So addition reaction is adding across the bond. It's electrophilic, isn't it? Because it's hunting out that electron-rich region. So yeah, it's going to be addition reaction. It's going to be electrophilic addition. So that's going to get us a mark. So far we're going to pick up marks for that. We're going to pick up marks for working out 12.2, working out the hydrogen was 12.2. We're going to pick out marks for working out the empirical formula. We're going to pick out marks for working out the molecular formula. So all of that is going to get us marks. That looks like we've got 1, 2, 3, 4. Minimum 4 marks. We might have 5 marks here. And the only thing we're left is with 2 possible structures. So, well, I said it has to be either a diene or a cycloalkene, because if it was an alkene, it would have this formula, CnH2n. So I'm going to go with, let's go with a cycloalkene. Ugh, that is ugly. Right, let's just put a double bond in there. So I would suggest that is one of the formulas, and you can check it by going, okay, well, what would we have? We'd have hydrogen. That would have one, two, three, four. So there wouldn't be a bond there. But all the other ones would have bonds. Da, 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 da. These would have two bonds coming off. Right. So one, two, three, four, five, six, seven, eight. Whoopsie. And then nine and 10. So that would be C10. So you see all the bonds, there'd be 10 hydrogens coming off, and one, two, three, four, five, six. So I could either just do the skeletal formulas. Did it ask for skeletal? It does. I don't think it matters. So there we go. That would be my one possible structure. I've got my cycloalkene, and then I would probably go with, let's just draw out hexane. I'm smashing two double bonds. So one, two, three, four, five, six. And then you want to put two double bonds. So we're going to make it a diene. So I'm just going to go there like one, what's that? Hexa 1,3 diene, something like that. And let's just check. There's the amount of hydrogen. Each one of these lines has a hydrogen attached. So there's five bad boy hydrogens. That's got one, two, three, four. Can't have any there. I need one hydrogen there. I need two more there. How many is that? One, two. I'm sure I'm missing something. Three. Four, five, six, seven, eight. I must be missing some hydrogen. Yeah, I'm missing two there. Nine and 10. Okay, there we go. So I've got 1,3 or hexa 1,3 diene, sorry, and cyclohexene. So yeah, uh they would be my possible isomers. So cyclohexene and hexa. Oh my gosh, I think I've messed this up. That looks absolutely filthy. Right, cyclohexene, hexa 1,3 diene. All right, and I think that's going to get us a lovely 6 marks. Sorry about the waffle. Okay, compound A is a halogenoalkane, named compound A. So you want to check the main chain. One, two, three, four, five. So we've got pentane, and then I've got two methyl groups coming off and a chloro. So it looks like, what am I looking at? Da, 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 da. So if you're numbering, uh, you want to give the everything the lowest number. So one, two, three, four, five carbons. So it's a pentane. And what we want to do is maybe go two mether, uh, two for dimether chloropentane. I might want to go three chloro, alphabetical, three chloro, two, four dimether pentane. So we're looking at, oh my days. So we're looking at three chloro, dimethyl. Oops, sorry. Three chloro. I need to number the methyls, don't I? Two, four, dimethyl pentane. And here we go. And that is going to get us a lovely mark. Okay, 6.2, compound A has a relative molecular mass, an MR of 134.5. The main isotope of hydrogen is hydrogen 1. The main isotope of carbon is carbon 12. Chlorine consists of two common isotopes, chlorine 35 and chlorine 37, of which 75% is chlorine 35. The mass spectrum of A was recorded when A was ionized by electron impact to form A plus ions. Draw on the figure 3 the peaks for the main molecular ions in the mass spectrum of A. So we know that they're going to be around 134 because this is the average of the isotopes taking into account the abundance. And we know that the hydrogen is always H1 and the carbon is carbon 12, but the variation here, the reason why it's 134.5, the variation is because of the fact that some of the isotopes have chlorine 35 and the rest of the isotopes have chlorine 37. We know that 75% of the isotopes have chlorine 35. So that tells me that 3/4 of the isotopes it has chlorine 35. So it's gone 3/4 of the way towards 134, which is why we have 134.5. And it's 25% going the other way. So 1/4 going up, increasing in relative molecular mass if it has chlorine 37, because 25%, 1/4 towards that would have to be 136. So that tells me that when it has chlorine 35, it's going to be 134. It's going to actually be, the whole number will be 134. And then when it has 37, it will be 136. So I need to draw two lines, one at 134, and that represents the chlorine 35. And that has to be 3 times the abundance. Okay, so 3 of the bars up. If that's 100%, that's 75%. And then the abundance of the chlorine 37 is only going to be 25%. So the total abundance is equal to 100. And when it has chlorine 35, it has a relative molecular mass of 134. When it has chlorine 37, a relative molecular mass of 136. And there we go. Okay, let's get into this question 9. A student has a 10 centimeter cube sample of 1 times 10 to the minus 2 mole per decimeter methanoic acid solution. The student's asked to dilute the methanoic acid solution to a concentration of 2 times 10 to the minus 4 mole per decimeter by adding distilled water. Which volume of water should be added? Okay, well, first of all, there's two ways to do this. So you could just say, what is that? That is the same as saying 0.01, 1 times 10 to the minus 2. And then they're going to dilute it, make it weaker. So it's going to go down to 2 times 10 to the minus 4, which is the same as saying 0.0002 moles per decimeter. So what we can do is say, okay, they're diluting it. By what factor are they diluting it? Well, we can find that out by taking the bigger number, the 0.01, dividing it by the smaller number. And what you're going to get is it is being diluted by a factor of 50. So they've tried to dilute it by 50 times, right? It started as 10 centimeters. And so in order to dilute it 50 times, they need to make it 50 times 10, and that is 500 centimeters. So how are they going to make it up to 500 centimeters? They're going to need to add 490. But it is, so that is the correct answer. It is understandable if you accidentally thought, well, actually they need to add 500. That would be understandable. The other way to show that they need to make the total volume of 500 is to use N over CV. So you could do that. N over C times V, and that will show you that the total V should be 500. And all you've got to do is work out the amount of moles in the original sample. So if we do this method, this is another method where you're going to use the triangle, and you might prefer that method because yeah, just use your triangle. So first of all, we've got 10 centimeters volume, and we have a concentration of 0.01. So we're going to divide 10 by 1,000, and we're going to get like what's 10 over 1,000? Is that 3 noughts and a 1? Let's check it out. No, it's just 0.01. So we're going to get 0.01, and guess what? You're going to times it by 0.01, which is the concentration. So, and you're going to get 1 times 10 to the minus 4. So that ends up with 1 times 10 to the minus 4 as your moles, as N. And then we know the new concentration is got to be 2 times 10 to the minus 4. So that's the same as saying that. So we need to do N over C equals V and find out what the new volume is going to be. So if I do 1 times 10 to the minus 4, which is zimoles, and I do that over the concentration, which is 2 times 10 to the minus 4, da, 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 divided by, and that equals 0.5. Hang on, you say, what's 0.5? Well, that is 0.5 decimeters, because you have to remember moles is in decimeters. And if you do 0.5 times 1,000 to put it into centimeters, you're going to find that it's 500 centimeter cubed. And again, this might make you go for the wrong answer, C, but it's telling us that if we want this concentration of 2 times 10 to the minus 4, you have to have 500 centimeters. So we should add 490 because there's already 10. So you're going to come to the same answer, that you need a total of 500. Now, I don't know which one of those ways is better. Maybe leave a comment which way you prefer. Anywho, or don't bother with that. Just get on and watch the rest of the walkthrough. Long 10. Which molecule does not have a permanent dipole? So really, you're looking at which molecule doesn't have a permanent dipole. So if you want to have a permanent dipole, then you need to be asymmetrical and have polar bonds. So we can see all of these have got polar bonds because bromine is electronegative, much more electronegative than carbon and hydrogen. So they're going to be polar bonds in all of polar bonds in all of these. But we can see here, this one is going to be symmetrical. And so this one, although it has delta negative, delta positive, because it is a symmetrical molecule, this one will not have a permanent dipole because they will cancel out. So bosh, that's our answer there. Okay, once again, I recommend you actually pause the video at the start of these before I give away the answer and have a go. Just put ABC down, see which one you think is right. Which is the major product of the reaction between two methyl butene and iodine monochloride? So, which of these is the major reaction? So, between two methyl butene and okay, well, what we need to do, um, I need to draw this out. So two methyl, butene, right? So we've got four carbons, right? And the double bond is butene, is between there and there. And then I've got a methyl group, lovely bubbly. And then this is like a methyl group as well. You know what? I could just write CH3 there. I was going to put the three C's around, but that's a methyl group as well. Let's just count one, two, three, four. That's fine. I need another hydrogen there. And then this is a methyl group here. So I could either, I could do that or I could write CH3. It doesn't really matter. Okay, so what's happening? This is very similar to when a bromine molecule, you might go, oh, but what happens with the iodine? It's very similar. Basically, this approaches like this. And what happens is it gets polarized. These electrons repel the electrons in this covalent bond. Now, chlorine's more electronegative, so chlorine's going to become slightly more negative, and the iodine positive. And now we just got to figure out which of these is the I going to join? Is it going to join here or is it going to join here? And then the chlorine's going to join. So you're really looking at the options are C or D because they're going to join across the double bond with electrophilic addition. So they're going to join across that double bond. And we're really just worried about, is it C or is it D? Well, it depends on the major product. So the first thing to know is that the iodine is going to be delta positive and the chlorine delta negative because chlorine's more electronegative and the electrons get repelled towards the more electronegative atom. When we're used to seeing this in your textbooks like that, and it's the exact same mechanism, but this time you've got I and Cl, but the same situation. So we're going to get a carbocation. Now, do you remember which carbocation forms? It's the carbocation that is going to form is going to be the one, the intermediate is going to look like that. And why is it going to be like that? Because this leaves two alkyl groups, which are electron donating, or they have an electroinductive effect, or whatever it is. They donate electrons to the carbocation and they stabilize it. So this is the more stable carbocation. So the I is actually going to join here first and then you're going to be left with your chlorine, which is going to join there in the second phase. So the answer is going to be C, and the reason being this is the major carbocation, so that is going to be the major product. This one over here is going to be the minor product, this D. Anywho, C is the correct answer. Let's get on to question 12. So, where am I? I'm over here. Okay. Question 12. Which statement is not correct? So we're looking for a false statement about the industrial preparation of ethanol by the hydration of ethene at 300 degrees. The reaction is catalyzed by an acid. That is true. It uses phosphoric acid, doesn't it? So that is a true statement. So that is not the right answer. The higher the pressure, the higher the yield of ethanol. Well, if we use a high pressure, it's going to shift to the side with the least gas molecules. I've got two gas molecules on that side and one G on that side. So this also, B is also true. So cannot be the correct answer because yes, if you increase the pressure, it will shift to the side with the least gas molecules, which is the ethanol. So we're going to get a better yield. So that is true. The higher the temperature, the higher the yield of ethanol. It's exothermic. You can tell from the negative sign here, right? It's exothermic. So if you increase the temperature, it's going to shift to the endothermic side because Le Chatelier says a reversible reaction will always shift equilibrium position to oppose the change you've made. So if you make it hotter, it's going to shift to the cold side, which is the endothermic side. So this is incorrect because increasing the temperature will give us a rubbish yield of ethanol. So this is the false statement and therefore is the correct answer. And then the final one, a low equilibrium yield of ethanol is acceptable because unreactive ethene is recycled. That sounds pretty plausible. Any unreacted ethene can be recycled. And so that would, yeah, that sounds true. Okay. Let's zing down. Which compound has the highest boiling points? What you're really looking for here, when you're talking about boiling points, you're looking for any giant structures. Oh my good gosh, I can't spell. Giant structures. What other things are going to have big boiling points? H bonding, dipole, permanent dipole, dipole. So you're looking at that like, what has it got? Butanal, yeah, butanal might have some dipole, dipole, but generally it's not got a lot going on. Butan 2-ol, yeah, that's going to have H bonding, isn't it? Because butan 2-ol is an alcohol. It's going to have that OH group. So we're going to get OH bonding or hydrogen bonding, sorry. But 2E, no, that's just going to be your Van der Waals or whatever. And one fluorobutane. Okay, so you've got a fluorine atom, so you can have a bit of dipole, but none of it is as strong as H bonding. We've got no giant structures there. So it is going to be this one with the hydrogen bonding. Okay, 14. Which statement is correct about the fractional distillation of crude oil? So we want to know which statement is correct. Zeolite catalyst is used. Now, I'm sure zeolite is cracking. It's that process. I may be wrong, but that doesn't sound like fractional distillation. Each fraction contains a mixture of hydrocarbons. I like it. That is the correct one. So when we talk about fractions like bitumen or we talk about diesel or petrol, it's actually just not one specific length hydrocarbon chain. It's a mixture of hydrocarbons of a similar hydrocarbon chain length. Okay. Gaseous fractions are formed by breaking covalent bonds. No, we don't break covalent bonds. We break IMF between the fractions. Okay. So that intermolecular forces, normally van der Waals. The fractionating column is hottest at the top. No, it's hot at the bottom where the bitumen comes off and it's cooler at the top. And yeah, that's wrong as well. Okay, cool. Just checking, just checking. Let's zing. Okay, 15. How many structural isomers with an unbranched carbon chain have the molecular formula C4H8Br2? Okay, let's draw that bad boy out. So if it's C4, this is a dibromobutane molecule, isn't it? So if we zing this, I'm going to write the different combinations and we're going to do each one. You get the idea. Right, so we've got two bromine molecules on a butane. So I could have 1,2 dibromobutane. Where else could I shift these bromines? I could shift one to here and have 1,3 dibromobutane. Yeah, don't know what I'm doing there. And oh, I could have 1,4 dibromobutane, 1,4. And I could also, yeah, I mean, if I do this, remember, you can't have 3,4. Remember, we do the lowest numbering. That just becomes 1,2 again. So we've already done that. And you can't have, you can't say, yeah, basically, you get the idea. It's always got to be the lowest. I can't have 2,4 because 2,4 is the same as 1,3. Ah, but I could have 2,3, right? I haven't done it where both bromines are in the middle. So I could have 2,3. So we know we've got at least four, but then I can also do this. I can then have it where the bromines are attached to the same carbon. So I could be like, oh, what if we put two bromines on this carbon? And that would be 1,1 dibromobutane. And then I guess I could have 2,2 dibromobutane. But you can't have 3,3 because that would become 1,1, 2,2. And I can't have 4,4 because that would become 1,1. So I've only really got those six combinations. And so the answer is going to be C. Beautiful. Right, let's zing down to 16. The Maxwell-Boltzmann distribution of molecular energies in a sample of gas at a fixed temperature is shown. Which letter represents the mean energy of the molecules? Right, well, the top of the peak here is the most probable energy, right? Yeah, the mean is always to the right of that. So D is the mean. Okay, yeah, D. Hold on. Number of molecules is up here. Energy is here. Yeah, so if you're wondering, is it A, B, or C, D? Number of molecules is here. and the energy is along the bottom. So you're getting more energetic as you go along the bottom and increasing the number of molecules up there. So when we're talking about energy, it has to be C or D. C is the most probable energy that a molecule has, and D is the mean, which is next to it. There we go. D is the correct answer. Okay. Zing. Ethanol can be made from glucose by fermentation. So we've got molecular glucose C6H12O6 going to two molecules of ethanol and two carbon dioxides. In an experiment, 268 grams of ethanol, MR of 46, were made from 1,440 grams or 1.44 kilograms of glucose, MR 180. What is the percentage yield? So there's two ways to do this. You can do the actual mass over the maximum theoretical mass, or you can do the actual moles over the maximum theoretical moles. I'm going to do the mass one, not that it really matters. So we made, oh, in an experiment, 286 grams were made. So our actual mass is 268 grams. So that is the actual mass. And I want to divide that by the theoretical maximum mass and times 100. So what is my max theoretical maximum mass? So what I've got to do there is work out how many moles of glucose I've got, and therefore how many moles of ethanol I've got, and times that by 46. So I had, oh my days, 1,440 grams of glucose. And if all of that reacts, I'm going to divide that by 180, which is the MR of glucose. So that's the MR of glucose. So let's do that. 1,440 divided by 180. And I get 8 moles of glucose, right? How many moles of ethanol should I make? Well, it's a 1 to 2 ratio. So times 2, I should make 16 moles ethanol. So if I want to do grams, find out the old grams, I need to do mass over moles times MR. So I want to do moles times MR. So 16 moles of ethanol times 46, which is the MR. So 16 times 46, and I get 736. So what I want to do is times that by hundreds, 268 over, what was it, 736. So 268 divided by 736 equals times 100 equals 36.41. 36.41. And that's the percentage. And that means my answer is B. Boom. Okay, let's move on. We are on. Ah! Sorry, pressed the wrong button. Everything flipped. 18. Which species could act as a nucleophile? So nucleus, phile means love, or like really attracted to. So nucleophile is attracted or loves nucleuses. Nucleuses are positive. So they love a nucleus. What sort of thing is going to be attracted to a nucleus? Something with a lone pair or a negative charge. So if we look at boron, the old Boronius, it's triangle planet. There's no, it's in group 3. So the way you can see it is all of its electrons are tied up in bonds with the hydrogen. So it's not that one. We can then look at ammonia is going to be the same, right? Because ammonia is tetrahedral, but um, it's got 5 electrons. So it's going to have 1 electron, but that's not going to be a very good nucleophile. Why? It's got a positive blooming charge. It's got 1 lone electron, doesn't have a lone pair because it's got 5 electrons in the outer shell. No, that's going to be pretty rubbish. It's going to be repelled by a nucleus because of that positive overall charge. Ba, 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 ba. Ooh, this is in group 5. So this is going to be pyramidal. and have that lone pair. So this could well be a nucleophile. Let's check out silicon. Silicon's group 4. It's going to be tetrahedral, right? Yeah, there's no lone pairs around silicon. So the answer must be C. Okay, because it's the only one with the lone pair that it can donate to something positive. So that is a nucleophile. Which statement is correct about polychloroethene? So what I want to do is draw out the monomer and then look at the different ones. So polychloroethene is going to look like this. You're going to have, it's basically an ethene molecule, right, which has chlorine there and hydrogen there. And all we're doing is that is the monomer, but we've taken that double bond away, haven't we? And we've opened it up. It's part of addition polymerization. So you know these from GCSE. So that is what the polymer looks like. So has the empirical formula CHCl? Well, no, it can't do, because if you, the simplest ratio, you've got three H's. You can't get that down to CHCl. So no, that's not the empirical formula. It decolorizes bromine. I've never heard of bromine. Sounds a bit dodge. It decolorizes bromine water. Well, there's no double bond there, so it can't decolorize bromine water. Its brittleness is reduced by plasticizers. This could be the case, all right? Aren't esters used as plasticizers? Anywho, yeah, that could be the case. So I'm going to check the next one and see which one sounds more plausible. Its polymer chain contains alternate single and double. There's no single and double bonds in the polymer chain there. That's nonsense. So it has to be this one. You might say, sir, didn't you know that one? Well, I wasn't sure whether polychloroethene was massively brittle, but you could definitely, if you add plasticizers to any polymer, you are going to make them more flexible. So it kind of had to be the right answer, right? You're going to reduce brittleness no matter what. So that was the correct answer. Always good to go for all of them, though, eh? Right, 20. What is the enthalpy of formation of buta-1,3-diene? We've been given enthalpies of combustion. So what you can do here, if you like to do this type of thing, what you can do is buta-1,3-diene. So we are saying what is the enthalpy of formation? So that's C4H6. That means they want us to work out delta H standard symbol, then an F or something, right? Yeah, I probably messed that right up. My writing is terrible. So we're going to need 4 carbons to make C4, and we're going to need H2 comes as a lovely H2, and there's 6 of them. So I'm going to need 3 H2s. So that's our equation. We're trying to find out the enthalpy of formation in their standard states. So we're trying to find out what the energy change is when you take these 4 carbon atoms. Why is that solid and that a gas? My God, I've had a brain meltdown. There's actually no need for me to be writing state symbols out. I don't know why I'm being a prat, but there we go. Um, Yeah, let's just get on with it, Tom. Right, enthalpy of combustion. So imagine we burnt carbon and hydrogen and we go this route. Remember Hess's law. No, regardless of the route taken, energy changes are the same. We don't know this, but we're being given this. So we've been told that we have 4 times minus 394, and that is for the carbon dioxide formation. And then, of course, if you burn the hydrogen, you're going to make water. And we're being told that I've got 3 times minus 286. So I want to whack that into the old calc and work out the total for the left-hand side. So that is 4 times minus 394. And that gives me 1,576 negative. And I want to add that to 3 times minus 286. And that gives me a total on this side of the Zeol equation, minus 2,434. And then enthalpy of combustion. So if you burnt that, you would release minus 2,546. Now, all you do is get an arrow and go clockwise around like that. And then anywhere where the arrows clash, and they clash here, you reverse the sign. So this becomes plus 2,546. So we just do minus 2,434 plus 2,546. And this gives us 112. Like that. So the answer, peeps, is that. Lovely jubbly. Let's move on. A gas cylinder contains 5 kilograms of propane. How many propane molecules are in the cylinder? And we've got the Avogadro's constant known as L. So this is nice and easy, isn't it? All we got to do is work out my moles of propane and times L. So number of the particles is equal to L, which is Avogadro's constant, times moles. I love to use N for moles. So it's L times N. So all I've got to do is work out N. How am I going to do that? I'm going to bust out the old mass over MR times N. And so I'm going to work out the moles by doing the mass over the MR. By the way, peeps, don't forget to pause the video and have a go. Super important that you're having a go at these on a scrap bit of paper, making it active, just using your calculator, then unpausing. Just chuck that paper away. Right, we've got 5,000 grams because 5 kilos is 5,000 grams. And we're going to divide that by the MR of propane. Propane, alkanes are CN, H2N plus 2. So C3H8, that's 3 times 12 is 36, plus 8 is 44. So we can do 5,000 over 44, and that is 123 divided by 44. That is giving us a lovely bubbly 113.6. And that is the moles. And now I want to keep that number in the old calc and times it by 6.022 times 10 to the 23. And I have a total of 6.84. So I'm going to times L, which is over here. I'm going to get 6.84 times 10 to the 25. And so that is going to be C as far as I can see. That is the answer. Okay, 22. We're nearly there. We're nearly there. Keep going. Do it now. Which sample of liquid has the greatest volume? We've been given D for density and we've been given mass. So you're using this equation. Density is mass divided by volume, which means as we're trying to calculate volume each time, I want to do M over D equals V. So mass over density equals volume. We need to change the units so they're the same. So this density is in grams. So I need to be doing 500 divided by 1,000 to put it in grams. So this is going to be 0.5 over 0.63. Smack that in the calc, see what you get. 0.5 divided by 0.63, and you get something along the lines of 0.79. I'm not going to write all the bits and rounding because hopefully it won't come down to that. This is 0.65 because we're dividing by 1,000, and that is over 0.8. Let's check that out. 0.65 divided by 0.8. What do we get? Ooh, this one has the greater density, so it's looking like B at the moment, but let's see, 0.81. This, 1.2, it's going to be this one, is divided by 1.33, and that equals 1.2 divided by 1.33. That's 0.9 something, right? 0.9, yeah. So that's like 0.9 something. And then this is 1.3. I don't think this is going to be 1.88 or something, right? 1.3 divided by 1.48 equals 0.87. So yeah, it's C. C was like 0.9. Okay, cool. The only tricky bit here was making sure to divide those by 1,000, but not dividing these by 1,000. They're already in grams. These needed to be converted to grams, and that's it. Bob's your uncle, Fanny's your aunt. Let's move on. 23. Which question represents an initiation step? Well, if I'm thinking initiation step, I'm thinking, or the one that you learn about, the old initiation step you guys learn about, you get the chlorine and it becomes chlorine free radicals or whatever. Yeah. So we're looking at something that's not a free radical, releasing free radicals. And look, this has already got a free radical. That's a propagation step. That can't do. This has already got a free radical. That's a prop. And this has got a free radical. That's a propagation step. The only one which starts without a free radical is this one and becomes free radicals is that one. So that is an initiation step. Boom. Right, guys. Don't forget, sharing's caring. Hit the like, punch up the bell, subscribe. Let's get to the marks. I'll check you guys on the next video.
You're still here? It's over.